Good evening, everyone.
Good evening, everyone. Good evening, everyone. Good evening, everyone. Good evening, everyone.
I'm sorry for the disturbance. I hope I am audible. So, today we'll be solving some assignment problems related to the Hahn Banach extension theorem and its corollaries. So, let's start with the true false. State whether the following are is true or false. Question number 1. There exists a non-zero continuous linear functional. There exists a non-zero continuous linear functional on L infinity. L infinity is the space of all bounded sequences, vanishing on the subspace C0, where C0 is the space of all sequences converging to 0. Sequences converging to 0. And L infinity is the space of all bounded sequences. We need to see whether we can find a continuous linear functional defined on L infinity. So it should be in the dual of the space L infinity and vanishes at C naught. So can anyone tell me is it's possible or not? Can we find such a continuous linear functional? If we could, okay, let's solution. If I define a functional f on C0 to R, where f of x, now x is an element in C naught, that means x is a sequence that is converging to 0. So I can write it as f of sequence xn. I denote it to be equal to limit n tending to infinity xn. So obviously for every element in C naught, fx is equal to 0. Now you can check that this f belongs to the dual of C naught, and since C naught is a subspace of L infinity, in fact closed subspace of L infinity, by Hahn Banach extension theorem, theorem there exists a continuous extension. There exists a function phi defined on L infinity such that its restriction over C naught is equal to F and its norm is equal to norm of F. This implies phi vanishes on C naught and phi belongs to L infinity star. That means phi is a continuous linear functional that vanishes on C naught. Therefore, this is true. This was just a direct application of the Hahn Banach extension theorem. Is it fine? Okay, then. Just a subspace. Since C0, the space of all sequences converging to 0 is a subspace of L infinity space, using the Hahn Banach extension theorem, we could find a continuous linear functional that is vanishing at L infinity, vanishing on C naught. Okay, let's move to next question number 2. C star is equal to L1. By C star, we mean the dual space of L1, dual space of C. Now the C is the space of all convergent sequences. Now, if this is true, that means let me mark it as 1. If first is true, then for every functional f defined on the space C to R, continuous linear, there exists some y in L1 such that f of x is equal to yx for every x in C. Now this is summation k from 1 to infinity yk xk, where this sequence yk belongs to L1 and the sequence xk belongs to C. That means xk is convergent. Now if I consider the functional that maps every sequence to its limit, let's see whether we can find such a y in L1 for that functional as well. Consider phi from C to R, where phi of x, which is equal to phi of the sequence xn, is limit n tending to infinity xn. Suppose C star is equal, okay, let us suppose C star is L1. This implies okay, this implies there exists y in L1 such that phi x is equal to summation k from 1 to infinity xk yk. Now norm phi is equal to supremum mod phi x by norm x for every x non-zero, since for every x in C, by this norm we have this uniform norm, mod phi x is obviously less than equal to the infinity norm of x, because limit n tending to infinity xn is obviously less than equal to supremum mod xn and sorry n in n, which is the sup norm of x. This implies norm phi is less than equal to 1, and since the constant sequence 1 belongs to C, and for this mod phi x by norm x is equal to 1, that means the supremum is attained, we get norm phi is equal to 1. Okay, here we had with norm y equals to norm f. This implies our norm y, this implies norm y should be equal to 1, and phi x is equal to yx for every x in C. Now if I consider the sequence, consider the sequence xn in C, where xn is the sequence such that it is 0 for all first n minus 1 terms, and after that it is 1. So this is nth position. Clearly this belongs to C for every n in n, and phi xn, this is xny, which is summation k from 1 to infinity xnk. This is, since first n minus 1 terms of this sequence are 0, so this is just summation k from n to infinity, and rest of the terms are 1, so this is equal to yk, which is obviously less than equal to summation k from n to infinity mod yk. Now since this is finite, this will tend to 0, since summation k from 1 to infinity is finite, because we know that tail of a convergence series converges to 0 as n tends to infinity. This gives us phi xn converges to 0 as n tends to infinity. But we know that what was phi xn? Phi xn was limit k tending to infinity xnk, and which is 1 for every n in n. Now this gives us contradiction. Therefore, this gives us a contradiction. Therefore, C star is not equal to L1. False. See, what we did, we started with an assumption that suppose C star is equal to L1. Now, if C star is L1, then every functional in C, every functional defined on C can be written as phi of x is equal to the inner product of x with y for some y in L1. So I assume, considering the functional phi, now I found an example of a functional phi which cannot be written in that form. I started with the functional phi which maps every sequence in C to its limit, and I have shown that we cannot find any y in L1 having norm 1, norm equal to norm of phi, such that we can write phi of x is equal to some inner product of x with y. So I hope you understood how we got the contradiction. To in order to give the find prove the contradiction, we use these sequences xn in C. Therefore, C star is not equal to L1. I hope this was fine. Okay, so let's move to the next question. The set of all those functions f in CCR. CCR is the space of all continuous functions with compact support defined on R, such that integration minus infinity to infinity ft dt is equal to 1. Is a closed hyperplane in CCR. And we know that a closed hyperplane on any nonlinear space is of the form f in all f in V such that phi f is equal to some constant alpha, where phi belongs to V star. This is the general form of a closed hyperplane. So in our case, this functional phi is minus infinity to infinity ft dt. If if this phi is a continuous linear functional, this continuous linear functional on CCR, then if I mark this as S, then S is a closed hyperplane. Can you just check and tell me whether this is a continuous linear functional or not? This function phi, I've defined phi from CCR to R. Phi of f is equal to minus infinity to infinity ft dt. Whether this is a continuous linear functional or not. If you think that it is a continuous linear functional, just try to prove it using definition. Show that mod phi f is less than or equal to some constant times norm f, and norm is the supremum norm because we are on CCR. Or find some example to show that this is not continuous. Uh, you can find some sequence Fn that is converging to some f in CCR, but phi of Fn is not converging to phi of f. Clearly, this is linear. Linearity is not the issue. The issue would be for the continuity of phi. Please check and tell me whether it is continuous or not. So this will be actually, this is not a continuous linear function. We'll see look at some one example of such a sequence. Let us see how. Now consider the sequence Fn in CCR, where Fnx is defined as follows. It is equal to 1 by n for all mod x less than equal to n. It is equal to 0 for all mod x greater than equal to n plus 1. And in between, we have this is between 0 and 1 by n. So this is a function having graph something like this from minus n to n. This is equal to 1 by n. From minus n plus 1 to infinity, this is 0. From n plus 1 to infinity, this is 0. And in between, we don't know about the curve, but all we know that it is continuous and its value is between 1 by n to 0. Now this gives us clearly, we can see that pointwise this is converging to 0 because as n tends to infinity, this 1 by n will tend to 0. So basically we'll be going something like this, then this, the sequence is something like this, and so on. It will converge pointwise to 0. Clearly, you can check that the sequence fnx converges to 0 pointwise on R. Now we need to see the convergence in CCR. CCR means with the soup norm. And what about Fn minus 0 soup norm? This is supremum mod Fnx for all x in R. And clearly, by the definition of the function Fn, the supremum is 1 by n. 1 by n. Now this converges to 0 as n tends to infinity. Therefore, Fn converges to 0 in CCR. Now we have assumed if this phi, if above defined phi is continuous on CCR, then phi Fn should converge to phi 0, which is equal to 0 because phi is clearly linear. We know that linear transformation maps 0 to 0. This implies limit n tending to infinity phi Fn is 0. Now see, what is phi Fn? Phi Fn is, how was our phi defined? Phi is integration minus infinity to infinity ft. So this is minus infinity to infinity fnt dt. So this integral is obviously greater than equal to integral from minus n to n. And from minus n to n, the function attains 1 by n. So this is just a constant. We come outside x, sorry, t minus n to n. So this is 2. This gives us phi fn is greater than equal to 2 for every n in n. That means phi fn can never converge to 0. Phi fn never converges to 0. Now this gives us a contradiction. This implies phi is not continuous and hence the set S is not a closed hyperplane in CCR. Is it fine? So in order to make this set S to be a closed hyperplane, it should be of this form: phi f equals to alpha for some phi in the dual of the norm linear space V. That means this phi should be a continuous linear functional defined on the norm space V. Now for our case, the norm linear space is the space CCR. Then and our given functional phi, if it was a functional, phi is defined something like this: the integration minus infinity to infinity ft dt. So if this phi is a continuous linear functional on CCR, then clearly by the definition this set S turns out to be the closed hyperplane. So clearly, linearity was not an issue. The issue was for the continuity of this functional phi. We have seen that this functional phi, it cannot be continuous because we could find a sequence Fn, sequence in the in our norm linear space CCR, such that it is converging to 0, but phi of Fn is not converging to phi of 0, which contradicts the definition of continuity, and hence this set is not a closed hyperplane. Therefore, the given statement is false. So the main important task was to construct this sequence in order to show that this functional phi is not continuously. So I hope this is fine. Let's move to the next question. Question number 4. Let V be a non-linear space and C is equal to B0R, the open ball centered at origin with radius R positive. Let P denote the Minkowski functional. We'll see how is it defined. Let P denote the Minkowski functional on set C. Then Px, or I should write PCx, I denote this as PC because it is depending on C. PCx is equal to norm x by R for every x in V. Now let's recall what do we mean by Minkowski's functional. Recall Minkowski functional. Let V be a non-linear space and C be a subset of V. We define PC a functional on V to R. PCx is equal to infimum of all those R positive. Instead of R, let me write it alpha because R is already fixed. Infimum of all those alpha positive such that X belongs to alpha C for every X in V. So, in order to find the value of PCX, we start with looking for all those alphas such that X belongs to alpha C. And taking the infimum of over all those alphas, we get the value PCX. In our case, C is the open ball centered at origin with radius R. So let's see how can we denote this PCX in terms of norm X and R. Solution. Let's start with a non-zero X in V. X be a non-zero vector in V. Then for every epsilon positive, which is less than r, we have norm of r minus epsilon x by norm x. So this is just scalar multiplication of x, r minus epsilon by norm x times x. Its norm will be equal to mod r minus epsilon. Clearly, since epsilon positive is less than r, so this is less than r. This implies r minus epsilon by norm x times x belongs to B0R, which is our C. This implies that x belongs to norm x by r minus epsilon times C. Now if I denote, let's denote the set S as all those alpha such that alpha positive such that x belongs to alpha times C, we get norm x by r minus epsilon belongs to S for every 0 less than epsilon less than r. This implies PCX, because obviously PCX is the infimum of all alphas in S. This is less than equal to norm x by r minus epsilon for every 0 less than epsilon less than r. Now since epsilon positive less than r is arbitrary, we get PCX is less than equal to norm x by r. Thus we can take this epsilon tending to 0. Let's mark this as equation 1. Now suppose alpha belongs to S. This tells us that clearly x belongs to alpha C, or we can say and alpha is non-zero. Obviously alpha is non-zero because S is all those alpha positive, na? We are by definition S contains alphas which are strictly positive. So clearly this is non-zero. So I can divide or we can say I can scalar multiply x by 1 by alpha. So this tells us 1 by alpha times x belongs to C. Now C is B0R. That means norm of 1 by alpha times x is strictly less than r. This tells us that alpha is strictly greater than norm x by r, because clearly alpha is positive, so mod alpha is equal to alpha. Hmm. Now since alpha belonging to S was arbitrary, so I can write alpha greater than norm x by r for every alpha in S. That means the infimum alpha in S is greater than equal to norm x by r. And what is infimum of all those alphas in S? This is our PCX. PCX is greater than equal to norm x by r. By first and second, PCX is equal to norm x by r. Therefore, the given statement is true. I hope this is fine. If you have any doubt in any step, please let me know. Please go through the solution once again. How we deduce that this PCX can be written as in the form of norm x and r. So we are done with true false. Let's move forward to some. So is my screen visible now? I think the sharing got stopped. So is it visible now?
Yes, visible.
Let's move to next. Answer the following type questions. Answer the following. Question number 1, A part. Let y be the sequence defined as follows. Let y equal to yn be the sequence defined as yn is equal to 1 minus 1 by n for every n. So that there does not exist any x in L1 with norm x equal to 1 such that the inner product of y with x is equal to norm infinity norm of y, where this inner product is just component wise multiplication. Yx is equal to summation k from 1 to infinity yk xk. Solution. Now let if possible there exists such x in L1. Let if possible there exists x in L1 with the L1 norm. L1 norm of x is equal to 1 such that. So what is infinity norm of y? This y is the sequence yn 1 minus 1 by n. Clearly its supremum will be 1 such that 1 which is equal to the sup norm of y is equal to the inner product yx. Now this is defined as summation k from 1 to infinity yk xk. Now this is equal to summation k from 1 to infinity 1 minus 1 by k xk. Clearly 1 minus 1 by k is strictly less than 1 for every k in n. So this is strictly less than summation k from 1 to infinity xk, because 1 minus 1 by k is strictly less than 1 for every k in n. This will be actually equal to n only when k tends to infinity. So for every fixed k, this is strictly less than 1. And this is less than equal to summation k from 1 to infinity mod xk, which is the L1 norm of x. Now L1 norm of x is 1. This gives us that 1 is strictly less than 1, which is not possible. Therefore, by contradiction, by contradiction, such x will never exist. So there does not exist any such x in L1 such that its norm is equal to 1 and its inner product with the sequence yn is equal to the sup norm of y, which is basically 1. Therefore, now this seems to us that why we are doing this, but this will be helpful for us further to show that the L1 space is not reflexive. The reflexivity helps us to prove many further good results. So we always tend to see whether this given space is reflexive or not. So this example will basically help us to see that the space L1 is not reflexive. Moreover, further we'll be looking at some other examples where we'll see which space is reflexive or not. So next part says that deduce that L1 is not reflexive. In order to prove this, we'll be recalling a corollary to the Hahn Banach extension theorem, the analytic version. Let's recall corollary to the analytic Hahn Banach theorem. You can just go through your notes or lecture videos. It has been done in the class that if V is a non-linear space, X naught is a non-zero element in V. So instead, I should write it as 0 not equal to X naught is an element in V. Then there exists a functional f in V star such that fx naught is equal to norm x naught and norm f is equal to 1. So we'll be using this corollary to show that if a non-linear space is reflexive, then for every functional in its dual, the functional should attain its norm. Let's see how. Solution. Since L1 star is the dual space of L1, is a non-linear space. Consider a non-zero functional f in L1 star by above corollary. There exists a functional phi in L1 star star such that f of f is equal to norm f and norm f, capital F, is equal to 1. Now if L1 is reflexive, now if L1 is reflexive, that means the evaluation map J from L1 to L1 star star is surjective, or we can say that it's a bijective isometry. Then for every f in L1 star star, there exists a y in L1 such that fg is equal to gy for every g in L1 star. That's how the functional j is defined. And instead of for every, let's consider the above f. This implies for above deduced f in L1 star star, there exists some y in L1 such that j of y is equal to f. That is, jy at any g is equal to fg for every g in L1 star, because jy is a linear functional defined on L1 star. That is, and how is jy defined? This is equal to gy. Gy is equal to fg for every g in L1 star. And since j is an isometry, norm y is equal to norm jy, which is equal to f, norm f, and we know that norm f is 1. Therefore, now this star, since star holds for every g in L1 star, this implies it holds for this f. Star holds for above f as well. This implies fy is equal to capital F at small f. Now this is equal to norm f, and from here we have norm y is equal to 1. Up, that is, fy is equal to norm f and norm y is equal to 1. Now since this f belonging to L1 star was arbitrary, we can say that we can make it as a note. If V is, so instead of L1, I can take any non-linear space V, which is reflexive. If V is reflexive, then every functional F in V star attains its norm at some point y in V such that y is a unit vector. Now this is a very good point to remember. Now we'll be using this. And above part A, in order to show that L1 should not be reflexive. Now if I consider the functional phi from L1 to R, phi x is equal to yx, where this y is the sequence yn defined in part 1, where yn is equal to 1 minus 1 by n. Clearly, you can see that. Clearly, one can see that this phi belongs to L1 star. Please try it yourself. Try to show that this is a continuous linear functional. Now, according to this remark, I can call it as a remark, it should attain its norm. So let's start, firstly see what will be its norm. So I claim that this norm of this functional phi is actually the sup norm of sequence y. Let's see. Now, for every x in L1, we have, where x is non-zero, we have mod fx, sorry, phi x. Mod phi x is equal to modulus yx, which is less than equal to summation k from 1 to infinity mod yk xk. Now this is obviously less than equal to the sup norm of y, summation k from 1 to infinity mod xk, and this is the L1 norm of x. This implies mod phi x by L1 norm of x is less than equal to the sup norm of y for every x non-zero. So by definition of the operator norm, this implies norm phi is less than equal to sup norm of y. And also xn is an element of L1. I define it as 0, 0, 1, 0, 1 at nth position and rest of the terms 0. This is nth position. Clearly this belongs to L1 for every n in n. This implies the L1 norm of xn is clearly 1 for every n in n, and phi xn by xn L1 norm. Obviously, this is less than equal to norm phi by the definition of operator norm for every n in n. This implies limit n tending to infinity mod phi xn. Since norm xn 1 is 1, so I'll just not write it. This is less than equal to norm phi for every n in n. Now let's see what is phi xn. Now phi xn count mod, this is equal to modulus yxn. So this is modulus. So since this xn is non-zero only at nth position, so rest of the terms in the summation will be 0. We'll be left with just the yn element, which is 1 minus 1 by n. Clearly, this converges to 1 as n tends to infinity. This implies 1 is less than equal to norm phi. And this 1 is actually the sup norm of 1 y. This is less than equal to phi. Hence, um, by first and second, the operator norm of phi is equal to sup norm of y. So, by our remark, we should be able to find a function, a sequence x in L1 such that its norm is equal to 1 and phi of x is equal to the norm of phi, which is the sup norm of y. This implies by above remark, if L1 is reflexive, then there exists some x in L1 with L1 norm of x equal to 1 such that this phi of x is equal to the norm of phi, which is equal to the sup norm of y. But we have seen in part 1, part A, in part A we have shown that there does not exist any such x. But in part A, we have seen that such x can never exist. Hence, L1 is not reflexive. Is this fine with everyone? How we proved that L1 space can never be reflexive? The main important point is this remark. We should remember that if V is a reflexive nonlinear space, then for every functional f in V star, there exists some point y in V with norm 1 such that it attains the norm of f. And we have seen that such an x will never can never exist for the case of the functional phi defined using the sequence y in L infinity given by yn equals to 1 minus 1 by n. So this part A helped us to prove that the space L1 is not reflexive. Is it fine? Please let me know if any of the step is not clear. I've tried to elaborate each and every step. Then also if any doubt, please. Okay. So let's move to the next question. In next part, we'll be showing that the space C naught, the space of all sequences converging to 0, is not reflexive using a similar approach. Question number 2, part A. Let y belongs to L1. Show that there does not exist any x in C0 where C0 is the space of all sequences converging to 0 with sup norm of x is equal to 1 such that yx is equal to the L1 norm of y, where this inner product is defined as summation k from 1 to infinity yk xk. So let if possible, such x exists. Let if possible, there exists an element x in C naught with sup norm equal to 1 such that the L1 norm of y is equal to yx, which is equal to summation k from 1 to infinity yk xk. Now, since x is in C naught, this implies xk converges to 0. This implies we can find a natural number n such that modulus xk is strictly less than 1 for all k greater than equal to n. Clearly taking epsilon to be equal to 1 and using the definition of convergence, this implies I can write summation k from 1 to infinity yk xk less than equal to summation k from 1 to infinity mod yk mod xk, and I can split this sum from 1 to n plus summation k from n to infinity mod yk xk. Now, this term mod xk is obviously less than equal to the sup norm 1. So in this case, we'll have less than equal to, and in this case, we have strict inequality. This implies overall we have strict inequality summation k from 1 to infinity mod yk. Now this is equal to the L1 norm. But we started with the L1 norm. This give us mod. This is strictly less than L1 norm of y, which is not possible. Therefore, there does not exist such x. Now again using this functional, defining a functional f from C naught to R, f of x is equal to yx, where this y belongs to L1, and using part A will show that C naught is not reflexive. Part B, deduce that C naught is not reflexive. Solution. Suppose C naught is reflexive. Then, by above remark, we have For every f in C naught star, there exists some x in C naught with the sup norm equals to 1 such that f of x is equal to norm f. Now consider the functional f from C naught to R, where fx is equal to y times x for every x in C naught, and this y and this y is some element in L1. Then there exists some x naught in C naught such that f of x, which is yx, is equal to norm f. Now let's see what is norm f. I claim that norm f is equal to L1 norm of y. If norm f is equal to L1 norm of y, in that case we know that such x can never exist. With sup norm of x equals to 1. Now I claim that norm f, you can see that this f belongs to C naught star is equal to L1 norm of y. Now for every x in C naught, mod fx is less than equal to, no. So this is equal to mod yx, which is less than equal to summation k from 1 to infinity mod yk mod xk. This is obviously less than equal to the sup norm of x times summation k from 1 to infinity mod yk. Now this is L1 norm of y. So this implies mod fx by norm x infinity is less than equal to L1 norm of y for every non-zero x in C naught. So by definition of the operator norm, norm f is less than equal to norm y. 1. Let's mark this as equation 1. Now consider the sequence. Consider the sequence xn, which is equal to signum y1, signum y2, sine of y1, sine of y2, and so on up to sine of yn, and rest of the terms 0. Clearly, this is a convergent sequence converging to 0. So this will belong to C naught. So mod fxn by the sup norm of x is less than equal to norm f for every n. Now since sup norm of this xn is clearly 1, because these values are either 1 or minus 1, and taking modulus is actually equal to 1, so the supremum will be 1. So this implies limit n tending to infinity mod fxn is less than equal to norm f for f. Sorry. Now, what is mod fxn? This is summation k from 1 to infinity xnk yk. Now, since xn is 0 after n. So these are first n elements, n terms. After n plus 1, all the terms are 0. So this is plus summation k from 1 to n signum yk. So any real number multiplied by its sign gives its modulus. So this is summation k from 1 to n mod yk. So this implies limit n tending to infinity, or instead we can write it as norm f greater than equal to limit n tending to infinity mod fxn is equal to limit n tending to infinity summation k from 1 to n mod yk, which is basically the L1 norm of y. So marking this as equation 2. By equation 1 and 2 we get, by first and second, we get norm f is equal to the L1 norm of y. That means, now if, let me mark this one as star, by star, if C naught is reflexive, then I should be able to find some x naught in C naughts with uh, sup norm of x naught equals to 1, such that fx, which is the inner product yx, should be equal to norm f, which is norm L1 norm of y. But in part A, we have seen that such x will never exist. Hence, the space C naught can never be reflexive. This implies, by star, there exists some x naught in C naught with sup norm of x naught equal to 1, such that the inner product y with x naught is equal to L1 norm of y. But in part A, we have seen that such x naught does not exist. Hence, C naught is not reflexive. Similarly, in next part, we'll be showing that C, the space of all convergent sequences, will also cannot be reflexive. So, is this fine? We have used the similar approach as we had done in the previous question. Question 3, A part. Let y belongs to L1. Y is non-zero. For every x in C, C is the space of all convergent sequences. Define yx is equal to summation k from 1 to infinity yk xk. So that this defines a continuous linear functional on C, and its norm is the L1 norm of y. Assumption. Clearly, now if I define f from C to R, f of x is yx. Clearly, you can see that this f is linear. And for continuity, we have mod fx is equal to mod yx, which is less than equal to summation k from 1 to infinity mod yk mod xk, which is less than equal to the sup norm of x times summation k from 1 to infinity mod yk, which is equal to sup norm of x times L1 norm of y. Therefore, mod fx is less than equal to times sup norm of x. Now this gives us continuity. This implies f is continuous and hence f belongs to C star. Now we need to show that its norm is equal to L1 norm of y. So by first, clearly, we get that the operator norm of f is less than equal to L1 norm of y. And similarly, as done earlier, taking the sequence x n to be equal to sin y1 up to sin yn and rest of the terms being 0. Obviously, this as this belongs to C naught, this will belongs to C1, C as well. We can see that the operator norm of f is greater than equal to L1 norm of y. As done, similarly as done in the previous question, we can see. And therefore, norm f is equal to norm y, L1 norm of y. That's what we needed to prove. We need to show that f is a continuous linear functional and its norm is equal to L1 norm of y. Next part, taking y to be a specific sequence in L1 defined as yn is equal to minus 1 to the power n by 2 to the power n. Clearly, this since summation 1 by 2 to the power n is a p series, so this will be convergent. Hence, this sequence belongs to the space L1. Show that there does not exist any x in C with sup norm of x is equal to 1 such that summation k from 1 to infinity ykxk, which is the yx is equal to 1. Solution. Again, we'll start with let if possible such an x exists. Let if possible there exists x in C with sup norm equal to 1 such that 1 is equal to inner product yx, which is summation k from 1 to infinity ykxk. Now this is less than equal to summation k from 1 to infinity mod yk mod xk, which is less than equal to the sup norm of x summation k from 1 to infinity mod yk. Now since sup norm of x is equal to 1, this is equal to summation k from 1 to infinity 1 by 2 to the power k. That's how the sequence yk is defined. And we know that the sum is equal to 1. on the left hand side and right hand side both are equal to 1. That means the in between inequalities were actually the equalities. This implies summation k from 1 to infinity ykxk is equal to summation k from 1 to infinity mod ykxk, and this is equal to summation k from 1 to infinity mod yk. Now since for every k we have the inequality less than equal to, but it is given that the sum is equal. So now since for every k in n we have ykxk less than equal to mod yk mod xk less than equal to mod yk, because sup norm of x is 1. These two equations tells us that these inequalities should actually be the equalities for every k in n. For every k in n. Now this tells us that xk is equal to mod yk by yk, which is equal to modulus. So modulus yk is basically 1 by 2 to the power k, and this is minus 1 to the power k by 2 to the power k. So this is minus 1 to the power k. This implies the sequence x is minus 1 to the power k. But x was an element in C. It turned out that x is the sequence minus 1 to the power k. Is it convergent? Is the sequence x convergent? This can never be convergent. No? This is an oscillating sequence between 1 and minus 1. So this can never belong to C. This gives us a contradiction. Therefore, by contradiction, such x will never exist. Again, we'll be using this function to show that C is not reflexive. Deduce that C is not reflexive. So suppose C is reflexive, then by above remark, there exists some x in C with sup norm of x is equal to 1, such that fx, where this f is the one defined in part A, fx is equal to norm f, and we know that where f is as in part A, since norm f is equal to L1 norm of y, this implies fx is equal to norm y, but, or we can write it as yx is equal to L1 norm of y, but in part B we have seen that such x cannot exist. Therefore, C is not reflexive. Is it fine? Next, we'll be looking at the problem related to integration over vector value. We'll be looking at a problem on integration of vector valued functions, or we can say that vector valued integration. For let V and W be two Banach spaces. Let A be a linear linear map from V, continuous linear map from V to W. Let phi be a function defined on closed interval 0 to 1 to V. That means phi is a Banach valued function. Be a continuous map. We know how its integral is defined. So part A, let y is equal to integration 0 to 1 phi t dt. Show that ay is equal to 0 to 1 a phi t dt. Solution. Now since A belongs to LVW, that means A is a mapping from V to W, which is linear and continuous. Now let F be an element in the dual of space W. Be arbitrary. This implies F composed with A is a continuous linear map from the domain of A, that means V, to the codomain of F, that means R. Linear and continuous. This implies F composed with A belongs to the dual space of V. Then by the definition of vector valued integration, by definition of vector valued integration, we have phi OA at any point y is equal to integration 0 to 1 phi of A at phi t dt. That's how we define vector valued integration. This implies f at ay is equal to 0 to 1 f at a phi t dt. Now since f is an arbitrary element on V star, I can write it as for every f in V star. Now again, by definition, this gives us ay is equal to 0 to 1 a phi t dt. Sorry, this is double star. This is what we needed to show. Part B. Let lambda positive be a positive real number. Define R lambda from V to R lambda at any point x is given by integration 0 to infinity e to the power minus lambda t ax dt. Show that R lambda is well defined and R lambda belongs to LV to W. That means it is a continuous linear map from V to W. Solution. For any x in V, we have R lambda x is equal to, now since this ax is independent of t, I can take it outside. This is ax, and this integral can be written as limit b tending to infinity 0 to b e to the power minus lambda t dt. We know that this integral is finite from 0 to infinity. So this is basically, this turns out to be equal to ax by lambda, which is finite for every x in V. And since lambda is strictly positive, so dividing it by lambda is not a problem. Therefore, R lambda is well defined. Now, since A is a linear map, using the linearity of A, we can see that R lambda is also linear. In fact, mod R lambda x at any point x, this is equal to modulus 0 to infinity e to the power minus lambda t ax dt. So this is R lambda x is an element in R. This is an element of W. So this should be norm. And this can be written as norm ax. This is norm of W. And rest of the term is a constant, modulus 0 to infinity to the power minus lambda t dt. We know that this integral is equal to 1 by lambda norm axw. Now, since A is again a continuous linear map, so I can write it as less than equal to norm A norm xv by lambda for every x in V. Therefore, R lambda belongs to L V to W because it is a continuous linear map. Is it fine? Okay, then let's move to the last question of this session. Question number 5. Let J be the let V be a Banach space. Be a Banach space, and the mapping J from space V to V star star be the canonical or the evaluation map. Be the canonical mapping. B denotes the closed unit ball. If you remember, we had seen in the last class that this V is reflexive if and only if JB is dense in B star star. Closed unit ball. We need to show that. Show that JB is closed in V star star. Solution. So in order to show that a set is closed, we start with a convergence sequence, taking all the elements in the set. We prove that the limit is also an element of that set. That means all limit points are in the set. So let Fn be a sequence in JB such that Fn converges to Fn V star star. We claim that this F belongs to JB. Now, since Fn belongs to JB, for every n in n, this implies there exists a sequence Yn in B such that Fn is equal to Jyn. Now, since we had seen in the last class that this function J is, this mapping J is actually isometry, since Fn is convergent, implies Cauchy in V star star, and this mapping J is an isometry, we get norm Yn minus Ym, this is the norm of space B, is equal to norm J Yn minus J Ym, which is norm Fn minus Fm. Now this converges to 0 as n and m tends to infinity, because Fn is a Cauchy sequence. This implies Yn is Cauchy in V. Now, since V is a Banach space, this Yn is convergent. So there exists a Y in V such that norm Yn converges to Y. And norm Y is equal to limit n tending to infinity norm Yn. Now, since norm Yn is less than equal to 1, because all Yns are in the set B, so this limit will also be less than equal to 1 for every, this is less than equal to n. This implies Y belongs to B. And since J is continuous, we should have Jyn converging to Jy. Now, what is Jyn? Jyn is the sequence Fn. This implies Fn converges to Jy. Also, we know that Fn converges to F. So, by uniqueness of limit, this implies by uniqueness of limit, we have F is equal to Jy, which belongs to JB, because Y is in B. Therefore, JB is closed subset of V star star. So it seems that today's session was a bit boring. Nobody replied. Is it so? So if you have any doubt, please let me know. Please don't make me feel I'm talking to wall. Okay, then, if you don't have any doubt, thank you so much for attending the session. We'll be meeting next Friday. Next Friday, hopefully, I'll be discussing the next assignment sheet. I think we are lagging behind. It's okay. We'll take some extra classes. Okay, then. Thank you.
Thank you.